A mixed reality training system for hand-object interaction in simulated microgravity environments. Section 1 Introduction. Microgravity simulation is crucial for several reasons. Firstly, it addresses the increasing training requirements for space missions. Secondly, it provides a means for the general public to experience the sensation of space travel on Earth. Hand-object interaction is vital in space missions. Therefore, incorporating hand-object interaction tasks within simulated microgravity environments on Earth becomes a very necessary training component to enhance space travelers' performance in space missions. Traditional microgravity simulation methods face limitations in replicating partial weightlessness and involving high costs, making them less accessible for widespread use. Mixed reality technology offers the potential to provide more immersive and realistic microgravity simulations compared to the traditional methods. This motivates us to incorporate mixed reality to develop a training system for hand-object interaction in simulated microgravity environments. Section 2 Method. The first model utilizes the leap motion device to accurately capture users' hand motions. Within our system, we incorporate two types of virtual hands. The tracked hands represents users' actual hand movements. The rendered hands is a visual representation displayed in a virtual environment. The second module detects collisions between the tracked hands and virtual object. If no collision occurs, the positions and orientations of the tracked hand and the rendered hand remain consistent. However, if a collision is detected, it indicates that the tracked hand has intersected with the virtual object, prompting the system to respond accordingly and manage the interaction. In this work, we propose a novel method by incorporating impulse-based simulation. This enables the consideration of sliding and rotational movements, resulting in improved stability during manipulation tasks. Section 3 Simulated Results. We assess the performance of our system by comparing it to a state-of-the-art open-source approach. We conducted the evaluation using a rectangular prism as the first object. The results demonstrate that our method facilitates easier manipulation of the object, while the alternative method proved to be more challenging. The second object is a slender rectangular prism. These results demonstrate the stability of our methods in grasping objects with different shapes. In addition, our system supports various hand-object interactional actions, including ball grasping, cube grasping, pinching, lifting, and gently pushing objects. More demos are shown in this slide. Section 4 User Study. The user study has three main objects: evaluating the system's effectiveness in simulating microgravity for space mission training, assessing its usability and accessibility, and investigating the effect of different gravity conditions. The study procedure begins with an introduction to the purpose of evaluating our system. They were divided equally into two groups, the veteran group and the beginner group. The veteran group undergoes a training session using our system, while the beginner group proceeds directly to the first stage. In the first stage, participants are required to perform 3 pick-up and place tasks on different objects, with each task consisting of 3 stages: manipulating, maintenance, and release. During the maintenance phase, participants are required to stay at 3 places for a minimum duration of 3 seconds. The data reveals that the veteran group outperforms the beginner group, requiring fewer attempts and less time to complete the task. These findings indicate that our system effectively aids beginners in rapidly adapting object grasping in microgravity conditions. In the second stage, all participants perform tasks using the state-of-the-art system CLAB for comparison. Figure 11 illustrates a comprehensive comparison between our system and CLAB. Subfigure A and B display the number of failed attempts and task completion time, respectively. The analysis of participants' response to the naturalist and efficiency question in the subfigure C reveals a significant difference in average ratings, indicating that our system provides a superior user experience compared to CLAB. This finding highlighting the positive impact of our system in enhancing the overall user experience compared with the state-of-the-art. In the third stage of our user study, participants use our system to perform hand-object manipulation tasks under different gravity conditions. Figure 12 demonstrates the majority of participants, over 83%, found microgravity to be challenging for hand-object manipulation, particularly in mid-air grasping tasks. Only a small percentage, approximately 13%, reported minimal differences, and one participant perceived no differences. This finding underscores the need for dedicated hand-object interaction system tailored to microgravity environments. Section 5 Conclusion. In summary, we have proposed a novel MR-based training system for hand-object interaction in microgravity environments. Our system incorporates impulse-based simulation to enhance the realism of interaction. Through a user study, we have evaluated the effectiveness of our system. However, there are some limitations that should be addressed in future work, such as the need for more realistic hand avatars and the integration of our system with a VR headset for an even more immersive experience. These enhancements will further improve the training and simulation capabilities of our system. Thank you for watching.